Uh, Welcome everyone to today's Tuesday's PCS seminar. Today we have Professor Peter Schmelcher who will present his recent work in his group in Hamburg. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Okay, yeah, thanks, Dylan. So as Dylan has announced, our today's speaker is Professor Peter Schmelcher from University of Hamburg. So Peter received his PhD from University of Heidelberg in 1990, where he was working with Lorenz Sederbaum, who actually has visited our center a couple of years ago before when people could still travel easily. So then Peter Schmelcher hold postdoctoral positions at the University of Heidelberg and University of California, Santa Barbara, where he was working with Walter Kohn, one of the authors of the density functional theory. And since 1996, he was a lecturer at the University of Heidelberg, and then an associate professor at University of Bonn, and later again an associate, faculty at the University of Heidelberg, and since 2010 he's a professor at the University of Hamburg, his current workplace, and he has really broad research interests, including ultra-cold atoms and the various aspects of ultra-cold atoms like Bose-Einstein condensation correlated out of equilibrium quantum dynamics, Rydberg atoms, transport and structure formation in time-driven systems, as well as fundamental aspects and electronic structure of systems in external fields, isoscopic and quantum transport through nanostructures, nonlinear dynamics and chaos theory, and also theory and application of local symmetries. And that's, I believe, what he's going to talk about today. So let's welcome our speaker. And Peter, the screen is all yours.
Yeah, thank you very much for the kind introduction. It's particularly nice to be here. Thank you very much for the invitation. Of course, in these days, everything is digital. So I'm very pleased to give this seminar at the Center for Theoretical Physics at Dijon. And I will be talking to you a little bit about a concept which we have been developing over the past 10 years. Actually, the first thought on these local symmetries came about in 2010, right away at the time when I was moving from the University of Heidelberg, as already said, to University of Hamburg. And at the beginning, you know, as it is, if you start some thought, you're not sure what it is does it carry along or not? But then over the first 2-3 years, it was going so and so. And then after 3 years, we had a kind of a thought which was very fruitful and carried then on. And meanwhile, this concept became a little bit of a small field for us of research, which is and has been developing quite frequently. So I'm going to be telling you about this today in this seminar, and about other more recent, maybe different aspects related to graph theory next week's seminar. So the idea is to look at local symmetries in wave mechanical systems including quantum systems, optical systems, acoustical systems. And mostly I will be talking today about at the beginning, quite simple aspects of theory, which then increasingly more complicated, and then also some first, maybe in quotation marks, applications. So this is the Center for Optical Quantum Technologies, where I'm working. Of course, not these days. These days is home office. The center is a combination of theory and experiment. So there's experiments on the ground floor, and the first floor is theory offices, and the second floor, the offices of the experimentalist. We do have also a small workshop and guest program, but again, these days, this is on the hold. Now, very briefly from the beginning, this work has been done in collaboration, mostly with some very intelligent and nice people. Christian Morfonius, Malte Röntgen. Christian Morfonius is an advanced postdoc, and Malte Röntgen is an advanced PhD student. They have been on the road since a long time, actually, Christian, since the beginning of the concept of local symmetries. And then we have a long-standing fruitful collaboration with the University of Athens, with Professor Diakonos, and at the beginning also with Dr. Kalosoumis at the University of Athens. Then more recently, experimental collaborations in terms of optics have been with Luca Del Negro at Boston University, and then also with Alexander Samait in optics at the University of Rostock, and on acoustics with the European Laboratory on Acoustics in Le Mans in France. And the project is currently being funded by the German Science Foundation, by the Deutsche Forschungsgemeinschaft. So what is it about? How is the talk structured? First, I'll give you a brief introduction and motivation. Why local symmetries? What is our motivation? Then I will give you in quite some detail our key first observation, which brought us on the road, so to speak, in terms of the existence of invariant non-local currents, which allow us to generalize the parity and Bloch theorem in the presence of local symmetries. And then, and this is a big block, which is kind of having everything in it, the more recent developments, also the theory and applications of local symmetries, and maybe a brief outlook and perspectives. So let me start with a motivation. Well, it may sound like carrying oars to Athens, talking about symmetries. Of course, we all know that symmetries represent the cornerstone and a very fundamental principle in physics. We can do a lot of things if we know already about the symmetry of a system, say a symmetric group in particular, maybe a Lie group, maybe a discrete point group. Then we can already make predictions about the system, since we have powerful mathematical tools, group theory and representation theory. And for example, in quantum mechanics, we can tell them about degeneracies, we can tell about multiplets. We also know how electromagnetic transitions take place because we have selection rules, and we can tell a lot about the system without doing any explicit computations. Also in computations, it facilitates the story, but in particular, also without computations, you can tell a lot. Now, symmetries typically, if you think about an atom that has rotational symmetry, continuous symmetry, molecules typically have, if there exist symmetries, molecular point group symmetries. Or if you go to extended systems, then this could be a periodic crystal, which has a discrete translation symmetry. Now, all of that, and this is very important to notice, are global symmetries. That is, the symmetry holds for the system as a whole, yeah, for the complete system. Now, if you look into nature, whatever you mean with that, in many cases, you see that things are more complex than just having a system which has a global symmetry. Many systems are composite and more structured than just one global symmetry. And that is why one could transit from global to local symmetries. That means we have a symmetry which holds in a limited domain of space and not everywhere in space. And that the system in that limited domain is coupled to the environment, but still maybe approximately or exactly in that limited domain, this local symmetry holds. One could view it in the way that the global symmetry is broken and it is locally retained. Now, these are a few pictures, what I mean. Yeah, this is a sketch of a molecule, of course. It's a sketch, I know, and there's lots of bonds to the outside, but you know, you could approximate, say, this is a six-fold rotational discrete symmetry. Yeah, then you have links to the outside. And again here, and again here. But overall, the molecule has no six-fold rotational symmetry. Or here in an extended system on a surface, you see that there's defects, but in between the defects, there is a kind of local symmetries, which are six-fold in this case, unit cells which are present here with that six-fold symmetry, but then there's defects in between. So globally, this is certainly not a hexagonal lattice, a 2D hexagonal lattice, because there is impurities or defects, but there is local symmetry. Of course, also here in a different sense, because you see there is local symmetry here, but then the system extends differently to some other local symmetry here, and so forth and so forth. So the question we put ourselves at the very beginning is, we know such a lot about symmetries if we talk about global symmetries. Is there anything we can tell from the beginning, from scratch, if we have only a local symmetry? Is there maybe something like a theoretical framework of local symmetries such that we can use it in order to make predictions on a system or better understand systems that have local symmetries? And then maybe in our kind of vision, can we develop novel structures which have different properties by designing local symmetries? Yeah. So, and what we had in mind, and that a large part of the time we were pursuing this, we are wave mechanical systems. And as you shall see in a minute, we start with a very simple basic setup. Yeah. So, but that is meant to be acoustics, and there have been experiments on acoustics on this already. This is meant to be optics, that is meant electromagnetic wave propagation, and that is meant to be quantum mechanics, like many, many different ways. Two examples being electrons coherently propagating in some nanostructures, or cold atoms in Bose-Einstein condensate state, or maybe even non-interacting ideally, or interacting and having then some external potential. But there's many others, of course, apart from the principal issue. Now, let me start with looking into local symmetries after motivating this. And the theme of this chapter is invariant non-local currents. Now that will be the result of the existence of local symmetries. I will go into that in a minute. And as a consequence of the existence of these invariant currents, we can show that we can generalize the parity and Bloch theorem, which you all know very well, which do exist in the presence of global symmetries. So let me start out with a very simple equation that is the Helmholtz equation with a complex wave field. I call it capital A. Yeah, and that's of course spatial dependent. I restrict myself at this point in time to a single spatial dimension. And of course, this equation applies in the parallax approximation to optics. Then this would be something like a spatially dependent refraction index, or it could apply to matter waves, to quantum mechanics. And then the U of x would be the stationary Schrödinger equation, correspondingly the energy eigenvalue minus the potential V, and A of x is the wave function. And in optics, this would be the electric field. In acoustics, this would be pressure fields, sound waves, which have a phase and a magnitude again. And we focus on scattering. One spatial dimension, everything very simple. So you could think, well, come on, this has all been solved. But there's a caveat to this. We look into potentials that look different from what might expect usually. Usually, if you have a symmetry, and this P stands for pi, for parity symmetry, and this T stands for translation symmetry, then you could have a global parity symmetry, like here, you see left-right symmetry, or a discrete translation symmetry, and they hold in all of real one-dimensional space. But then, if you go to global symmetry, to local symmetries, from global to local symmetries, you see what you can do is you can restrict that domain, and you can have a potential which is reflection symmetric in the domain D1. And another part of the potential which is reflection symmetric in domain D2, but not overall on the whole real axis, only locally. And the same thing you see here, translation symmetry, only locally, but not globally. Now, if you think about this, of course, you know, this domain D1 is mapped onto itself, obviously in the operation of reflection on this domain. And here the same thing. But you could have something like gapped local symmetries, where you map from D to D bar with something else in between. And the reflection axis is here, and you map that part to that part, which is obviously the potential reflection symmetric. And similarly here in the local translation symmetry case.
Sorry, Peter, to interrupt.
Yes.
Is that possible with analytic functions, or do you have to break analyticity?
You have to break analyticity.
Thank you. Thank you.
Yes, very good question. Yeah. So now, if you overlap, if you cover real space, yeah, with local symmetries, you know, so here there were gaps, there are no local symmetry. But you see here that I covered all of real space with kind of domains which are involved in local symmetry operations. You know, here's a parity, here's a translation from here to here. So this is what we call completely locally symmetric. So maybe not to mix up with compact localized states. I will be talking about compact localized states next week, but this is completely locally symmetric potential. And then, you know, what in the course of time, what we found out, a class which is particularly intriguing, interesting, which is not shown here, is so-called overlapping local symmetries. You know, this is if the domains would overlap, yes, something like this on top of each other. Here there's a local symmetry, and here there's a local symmetry. That is really something which has interesting features. Okay, so this is what I mean by local symmetry. So let's put in a little math. Yeah, very simple, but still it is instructive. We do define a symmetry operation. We go from X to X bar, and then this symmetry operation, very simple, is linear. It's sigma x plus rho. Now, if sigma is -1 and sigma is +1 and alpha is correspondingly chosen, this will be an inversion through alpha, or it will be a translation by L. Then I assume that I do have a local symmetry. So U of X is U of f on X, that's the invariance, locally for an X out of D. Yeah, remember there were these domains where we had the local symmetry, and for that domains I ask that my U of X invariant. If D is R, the whole real axis, then this is a global symmetry. Yeah, otherwise, and this is the case which I'm interested in, it is a local symmetry. Now, of course, f of D equal D bar is in general different. So that's if you map from here to here, but of course, for example, if you map from here to here, but here, of course, D1 is mapped onto D1. So let's look at this symmetry operation. We assume that the potential is locally symmetric. And then maybe in retrospective, let's do the following. Let's build the following quantity. The wave field at X bar, remember, X bar is the symmetry transform point. A wave field X bar, the second derivative of the wave field at X, minus A of X, the wave field at X, and the second derivative at X bar. If you take this and you use the very simple, the Helmholtz equation, and do a little bit of algebra with some small tricks, minor tricks, then you find out that this is 0. Okay, you have explicitly using local symmetry of U here. Now, it turns out, next step, that you can write this quantity as a total derivative. Yeah, and we call this quantity, which is then used Q, and dq to dx is the derivative. Sorry, and you know, then this means that in the domain we consider with that given local symmetry that Q is constant. So in this sense, it is spatially invariant, constant in X in this domain. So A of X, A prime of X bar minus A of X bar times A prime of X is an invariant. Now, if you repeat,
sigma,
I'm sorry?
What is sigma in this equation? In front?
Yes, sigma is either -1 if it is an inversion, or it is +1 if it is a translation.
Thank you.
You're welcome. So then you do the same procedure, not with A and A double prime, but you do it with A star and A double prime. So the complex conjugation, and you find out that Q tilde, this is the second quantity, is also an invariant. Yeah. So we have Q and Q tilde who are built out of the wave field, locally constant in the domain of local symmetry. Now, you know, I'm sorry, this is not a local quantity. It is a non-local quantity because there's two arguments, X and X bar. So you might want to call this invariant non-local currents. The dimensionality is that of a current. It's a derivative of the wave field times the wave field. And you might want to put an H bar here if it is quantum mechanics. And this, or you might call it invariant two-point correlators at symmetry-related points. Yeah, that's kind of how you could call it. So now, of course, I have been specializing to one spatial dimension. In one spatial dimension, we have global current conservation. Yeah, that is probability in the quantum mechanics case, energy in the optics or acoustics case, although acoustics is quite dissipative, at least macroscopic acoustics. So then we have the conservation of this all very well known current. And then if you do a little algebra with the Q's and the Q tildes, it turns out that the 2-point correlators are linked to the single, to the local current in the way that Q tilde absolute value squared minus Q absolute value squared is sigma times J squared. So the global local current. So these are connected. Yeah, you might wonder a little bit, this is a 2-point argument, this is a 2-point quantity. So why does this end up in a single point quantity? That comes out in the algebra in the course that there is currents at x bar and currents at x, and of course they're equal. So this is how this expression kind of emerges with a little algebra. Okay, so what we have shown now is, well, there's local symmetries, and of course, locally symmetric wave fields are connected to the outside. So that means they are there is no global symmetry, and things might look completely unsymmetric. If you inspect the wave field itself, that's important to know this. If you would look by eye at the phase or the magnitude of the wave field, there wouldn't be any information about the local symmetry. But again, these correlators here, they carry the information of the local symmetry. Now, the question you could pose, and that's actually what we did some years ago, is does that help us to generalize some of existing symmetry relations? And you all know very well that if there is global discrete symmetries, we have the parity theorem, so the boundary conditions respect the symmetry. So we have either even or odd parity states, or in case of the Bloch theorem, in case of the discrete translation symmetry, we have psi of x is e to the ikx times the periodic function, the Bloch function phi k of x, or having this translational phase involved. So this is what we all very know. So now what's up now in the case of local symmetries? Yeah. Now, well, the goal would be use those invariants, which are nice, to obtain a definite relation between the wave field at a of x and maybe possibly at a of x bar. And that is indeed possible. Again, with a little piece of algebra, you can show that the wave field at x bar, and that's the symmetry transform point, just to remind you, is given by the wave field at the original point a of x and a star of x by this mapping relation. Note again, Q tilde and Q in the presence of the local symmetry are invariants. So that's a mapping, yeah? That's a mapping of the wave field in the presence of local symmetries from the point x to the point x bar. So the invariant non-local currents Q tilde, they give you the mapping of the field amplitudes, and they give those actually in the presence of local symmetries, but of course also in the case of global symmetries. I will come back to that in a minute. So this is a generalized transformation of the field, and it is a kind of what carries over, or what remains from symmetry if you break the symmetry from global to local. Now, you have to note the following. If you restore global symmetry, then the Q will vanish. Yeah, that you can show. That means Q is kind of a measure for the breaking of the global symmetry. And if you put Q equal to 0, then you get what you have down here. A at x bar is Q tilde over J over A of x, and that's an eigenvalue relation. And this eigenvalue becomes what you're used to in case of parity plus minus 1, or in case of the Bloch theorem, the phases. Yeah. So Q equal to 0 is a means global symmetry, back to the case which we used very much. Q unequal 0, non-vanishing, means locally broken symmetry. And in this sense, Q is something like a symmetry breaking parameter. Well, one has to distinguish. I wouldn't call it an order parameter. We know very well that this has a slightly different meaning. It would characterize a phase, maybe a quantum phase, yeah. And but in certain cases, we have shown that this is even amounts to a kind of more than just a symmetry breaking parameter. Now, so this is so far the background. This was something like status 2014 when we were kind of realizing this. And then on the very theoretical background, no, not in terms of progressing further towards applications of this, but in terms of theoretical background, we have had a number of other papers because we felt a little bit, do these invariant correlators allow to reformulate theory in a more extended sense than what we have been doing and what I have been showing you so far? Now, the answer is yes. And you can do, and this is really a shortcut now, you can develop some super Lagrangians where you can relate two Schrödinger problems. So you make a bigger Lagrangian, which has several entries, several fields, and you ask for the symmetry of the super Lagrangian, and you do a variation under SU2, and then what you get, and this is, you get a generalized continuity equation. And this generalized continuity equation is written down here with the two fields. Now, if you go back from this generalized continuity equation is, so to speak, the umbrella from which you can derive what I have been showing you so far. Because if you specialize to 1D, if you go to local symmetries and constitute a relation between V1 and V2, then you get the invariant correlators as a special case. But this one is giving you the channel framework. And now that can be generalized to an n-state super Lagrangian, and it can be generalized to n-body interacting systems. So far, there was no interaction. Here there is interaction, but that cancels out in the course of the derivation. And you can put it even on the level of BBGKY, the Born-Boguliub of Green, Kirkwood, and Ivan hierarchy of correlators, and develop an integral formalism for these correlators, which is kind of a bit of abstract, but also insightful from the theory side. And actually, this might also be the starting point if you think about generalizing things, for example, in Bose-Einstein condensates, where you have nonlinearity on the mean field level. If you want to include interactions in a systematic way, I guess this is the way to go here, which is actually this JCP from 2017. Okay, so this is the theory side, yeah. But over the years, we have been moving forward with a number of different applications in kind of theory applications, but also experimental implementations. You shall see in a minute. So let's step back for a second, because we want to embed this into the overall picture of what we know a little more. Yeah. So locally symmetric or completely locally symmetric or overlapping local symmetrics, material structures kind of generalize the notion of what we know, crystals, periodic or aperiodic crystals, say, for example, quasi-crystals like Fibonacci, Thau-Morse, others which with different classification of their spectral structure. Now, yeah, periodic crystals have a lot of symmetry, global symmetries. Quasi-crystals have no global symmetries, although, you know, after a certain iteration, you're almost back to global symmetry, but they have a lot of local symmetry. And actually, we've been analyzing this local symmetry in detail and how they go and how they overlap. And it's turned out that this is kind of fancy because you can develop a kind of local symmetry, quasi-periodic dynamics. So how to map symmetries onto each other in the course of the generation of quasi-crystals. Then on the other side, in the case where you have no symmetries at all, typically you would think about disordered systems. And then if you allow myself, I would consider locally symmetric materials to be somehow a bridge between those. Yeah? A bridge between the completely disordered and the periodic or quasi-crystals. So you can do, and actually we did this, look at a disordered system and systematically introduce more of symmetry and analyze, for example, the statistical properties of these systems. I will have one transparency towards the very end of this presentation. Okay, now what were the steps which we have been pursuing? There was one thing, since we wanted to applications in optics, we developed a discrete formalism. Now, it turns out that the invariants, the continuity equations, and all these things, it's not totally straightforward. You can't just discretize the Schrödinger equation or the Helmholtz equation and then get everything in the discretized version. It's not that easy. You really have, there's some peculiarities, and you have to follow a true discrete formalism. And this is what we did for applications in optical setups. We have, for example, coupled waveguide lattices or other systems. Then there is, of course, the question, if I have local symmetries, are these of any use if I want to do computations? Like in band structure, periodicity exploited, you have the Bloch cell, and you have the Bloch theorem, and you readily go to the band structure calculations, which exploits the discrete translation groups and the structure of the unit cell, of course. This is what is in here, how to exploit local symmetry for computational strategy. Then there was a PT, generalization, and then there is a periodically driven, explicitly time-dependent systems, where the Qs include a time integral over a period of the driving. So this was meant to periodic driving, not general pulse driving, periodic driving. And then there's an aspect which I didn't draw your attention to so far, but it is a nice one to my personal opinion. You know, if you don't know what your system looks like and you can analyze your wave field, detect it, measure it somehow, you can detect with these building these correlators, you can detect local order. Because again, if there is a local symmetry somewhere, the wave field will have this invariant correlator. That's it. And so you will get immediately information that there is local order if you measure the wave field and build the correlator. And I will come back to that soon. So applications. Quite at the beginning, you see this were papers 2013. We were interested in photonic multilayers. So a slab, a sequence of slabs of different refraction indices, 2D, and we consider in the paraxial approximation the electromagnetic wave propagation, and which is then the Helmholtz equation, coming back to the previous equation. And then this allowed us to kind of, this is theory at this point in time, to kind of inspect the wave field a little closer. And we learned a lot from that. From the wave field itself, in the presence of local symmetries, you see here a sequence of locally symmetric slabs. And the domains of local symmetries, which are multiple here, and the in-out electromagnetic field, electric field here, the wave propagation in this photonic multilayer system, it turned out that if you look at the wave field itself, you don't see anything, that there's a local symmetry. I said that already. But then if you look closer, you can see that the invariants give you a key aspect to this. For example, if you're interested in perfectly transmitting resonances, yeah, you want to have the whole slab to be transparent, transmission 1. Then it turns out that this corresponds to a sum rule on the invariant correlators. And these sum rules give you a classification of the types of resonances. We call those symmetric perfect transmitting resonances and asymmetric perfect transmitting resonances. And they distinguish by their wave profile and the rules on the wave profile. So the Qs are very good for a classification of perfectly transmitting resonances. So that's one good thing. And actually the first experiment, which was then published in 2015 on this, in order to verify this, was a macroscopic, this is a 1 meter device, a macroscopic acoustics experiment. So this is a pipe, you know, and it has a source and impedance sensor where you emit the pressure waves, the sound waves, and it has these openings over here, and the openings are, so to speak, defined locally symmetric domains, and here two ones, and you have an end, an anechoic end which absorbs, yeah. And then we were interested in measuring the Qs, so the wave profile. Now, the good thing is here, you know, I didn't emphasize maybe enough, the Qs are complex. This means if you want to do a measurement, you need not only to know the magnitude of the pressure field, you need to know also the phase, but you know it because you know the phase at the source. So this is nice in this acoustics experiment. Not every optics experiment has the full information about magnitude and source, but here you have the full information. So, and then what it turned out, the problem with this macroscopic acoustics is that they're very lossy. So that means we have put into the theory the loss. And at that time, 2014, it was a bit of a surprise to us that the standard loss term, which describes the relevant loss in acoustics, doesn't impact the invariance of the correlators at all. Yeah. So the invariance of the correlators is maintained fully. And that you see also here, yeah, where you see the experimental data and you see the Q magnitude and the phase of Q, and you see they are locally almost practically flat for different frequencies of the source of the sound waves. Now, what you also see is that at the same time, there's harsh damping, yeah, you know, half of the amplitude is gone. But you look, this would have been a PTR, a perfectly transmitting resonance, and this is another one, but then the real signal goes like that, but it agrees very well with the damp theory, yeah, and so we have a nice agreement, and at the same time, you see that the real part and the imaginary part of the wave profile is shown here. Essentially, it has nothing to do with the local symmetry, except you see here, here's the real part at the resonance follows the local symmetry, which you can show actually. So you can distinguish between phase and magnitude and what follows in what kind of resonance the local symmetry. Now this is, and actually I didn't emphasize enough, Olivier Richoux and Yorgos Theocharis are people from Le Mans, from the European Acoustics Laboratory. They have done these beautiful experiments, and since then, 2014, we have an ongoing collaboration, very fruitful. Those people are true experts in wave mechanics. So, optics. Now, this was a collaboration with Alexander Samait. Actually, I forgot the reference. This was a laser photonics review in 2019. And you know, this is set up with photonics waveguide lattices. So this is indicated here. And you can prepare a globally symmetric, you know, this is a globally symmetric parity, reflection symmetric setup. You can do local symmetries in these waveguide lattices, like here is a symmetry and here is a symmetry, or you can do no symmetry like the one arranged here. And then if you look at the wave field, and this is, you know, time corresponds to the Z direction here in these setups in terms of Helmholtz equation, you feed into one of these waveguides and look into the spreading, yeah? And in the wave field itself, you don't see any symmetry because this is a kind of a dynamics experiment where we feed in one waveguide and you look into the propagation. You neither see it in the global, local, or no symmetry, but if you go back to the theory which we have been developing for discrete systems, and now I just ask you to believe me, then you see the following here. If there is global symmetry, there's a nice agreement between theory and experiment. And global symmetry, it's just indicated here by this matrix off diagonal, which means it's a reflection symmetry with respect to the center of the waveguide array. Photonic waveguide lattice array. So then if there's no symmetry, you see that there's a severe deviation between this Q term, which characterizes the symmetry breaking, and the other term, which is responsible for this symmetry. And then you see if again, actually this goes back again to the discrete formulation, linking to the cues which I have been explaining to you previously. And then if you go to the local symmetry, then you see that there's nice agreement between these two terms, which is the indicator again for a presence of a local symmetry. So verification both in acoustics, wave mechanics, and optics. And yeah, so this was in 2015. No, this was from 2019, the experiment. And meanwhile, between 2015 and 19, we started this very nice collaboration with Luca Danecro at Boston University. And we got more and more interested out from that analysis on quasi-periodic chains into local symmetry analysis of quasi-periodic, well-known, vastly investigated quasi-periodic systems, such as the Fibonacci quasi-periodic chain. And what I show you here, and I admit this is a bit of a crowded picture, what I show here is the following. First of all, you see this is just the binary sequence of the Fibonacci chain. It is here a chain of finite length of 144 elements. Yeah? And above here, this stick spectrum is the square root of the length of the local symmetry domain. Yeah. So if I have here at one spot, I can have a local symmetry here in this quasi-periodic chain. If it would be big, then it would be a big stick, a large stick. If it would be a small domain, it would be a small stick. And you see that the biggest stick is here because the largest symmetry comes about here. This comes with the Cayley theorem and stuff, which is almost completing the symmetry. I don't want to go into that one due to the lack of time. But what you see here, so this is the symmetry domain, and this is the lattice itself. And then what you see here, the big graph, is the energy label index. Actually, that's the one here. And the states. So the gray picture here is the eigenstate, yeah, over the lattice. Yeah, this is the lattice. This is the energy labeling index, nu, and what you see is each eigenstate. Yeah, just you see it's pretty much delocalized, but certainly not homogeneously delocalized by no means. There's dark spots. You see, almost black ones. And there's pretty much wide regions, yeah. And the red stuff is the quasi bands of the Fibonacci chain, the energy bands, yeah. So this is the energy here, yeah, which is shown here. So you see also that the quasi bands have gaps. You like, for example, here, this state here has no amplitude in here. It has only amplitude at the edges, yeah, like the one here at the right edge, for example, this one at the left edge here, yeah. So you see that there's edge states and there is band states, and the edge states are, for example, here in the quasi band gap, yeah, or here, yeah. Now, what we have done is a very careful local symmetry analysis based on a real space approach, and that allowed us to control the edge localized gap states. And this theory is based on the following fact. Yeah? It turns out that if you go to the regime of large contrast, yeah, and actually, you know, the contrast is CSV over H. V is the on-site energy and H is the hopping. If you go into that, then you see, and then you can lower systematically the contrast, then you see that the eigenstates localize on domains with local symmetry. And this was the point where we said, okay, this is where we come into play, because we developed a theory of local resonators with local symmetries that are coupled to the environment, and treating that with a higher order degenerate perturbation theory, because this is a very delicately degenerate system. And that connects these resonators to the environment and allows us to understand, for large and intermediate contrast, the localization properties of those eigenstates, on the chain. Yeah. So you understand why this is dark and this is dark, because there's local resonators with local symmetries coupled to the environment. And you can this way also control the edge states, the appearance of the edge states, and even design how to shift around the edge states. That is meant by this local symmetry augmentation principle. So we know how to add a side, individually, to put edge state back into the quasi-band or to take it out of the quasi-band and so forth. So you have a pretty good control with this local resonator theory on how to modify these quasiperiodic chains to get controlled edge states and therefore also controlled transport. So this is a very brief look on a very recent work. Now this goes back to 2019. This work is published last year. Of course, and I mentioned this when there was this kind of mentioning of disordered systems. You could start with a disordered system and gradually introduce order, introducing local symmetries. And this is done here statistically. This is not a single device. This is a statistical average. So you average over many devices where you introduce gradually more and more symmetry domains. This is the number of symmetry domains. This is from left to right, increasing disordered strength. And what you see is from the completely disordered system to the local symmetry case, what you do is you diminish the localization properties. This is here shown for two cases, actually for the inverse participation ratio here, which is a well-known measure for localization, and another one here, which is less known, and actually it is the Friedel sum, and we have been modifying this Friedel sum to cumulative Friedel sums to get a measure also for fragmentation and not only for localization. So these two measures together tell you systematically, if you go from disorder, how the statistical properties change. You see this sudden jump if you introduce local symmetry down to smaller values, which means the delocalization and of the statistical eigenstates. And then if you increase D, making more and more smaller domains, you go back to the disordered case, like here. And this is also natural understanding. The smaller you make the local symmetry domains, the more the system gets disordered again, in this sense. Okay. Yes, let me conclude with this. I hope I could show you that local symmetry is a kind of a bridge between disorder and complete regularity in the sense of global symmetry or quasi-periodicity. It is a nice bridge and as such a very good starting point to ask reasonable questions. It took us a while to ask the right ones, or whatever that means, to ask ones that later on lead to fruitful results. Now, there is already a start of a theory of local symmetries beyond the standard symmetry formalism. At some point, we felt whether it might be possible to reformulate in terms of correlators quantum mechanics and describe quantum mechanics principally from that point of view, but that's an open question, maybe a too far-reaching question. But certainly local symmetries can be used as a quotation marks design principle for complex systems. They have certain structures and tunable properties. And again, there's a difference between having a few locally symmetric domains in an otherwise random system, or having complete locally symmetric systems, or having overlapping locally symmetric. These systems respond very differently to any input which comes along. So in some sense, local symmetry is a degree of freedom for the design, certainly. It might be also, if you go more abstract, considered as a dynamical degree of freedom. Of course, and I've shown that wave propagation is, of course, crucially modified in locally symmetric media, but there is ways to get that done and to design resonances and to use local symmetries to have more flexibility compared to the heavy constraint of global symmetry, so to speak. Now, of course, systems in nature that kind of undergo, maybe in particular with dissipation, the process of structure formation, those systems may spontaneously form local symmetries. And that's one very beautiful example here. This is a result of molecular dynamics simulations in this paper. And you know, you see out of a gas, what happens is these interacting systems, anisotropically 2D interacting molecules form domains of local symmetries. You see here there is kind of a layered structure of local translation symmetry here and here, but you see also that there is kind of fivefold symmetries here and here, and some kind of unit cells combining together, and then another symmetry over here, and maybe some disordered transient regions somewhere else. So yeah, that's a kind of known and it can develop spontaneously. So you can have the emergence and formation of local structures coming from out of equilibrium and relaxing to a maybe metastable state, but that could be extremely long-lived. I mean, Bose-Einstein condensates, as they are used in quantum determined gases, are certainly also metastable states, and you can do a lot of physics with metastable states. And that point I mentioned already, and that one I mentioned previously. So I would like to thank you very much for listening.
Thank you, Professor Schmelcher, for this wonderful talk. Let's thank our speaker. So we have